As we continue, we're going on into Chapter 7, the basic concepts of algebra, but we're not going to be doing all of the topics. I just wanted to alert you that these are available, and we're going to be skipping Topic 1, which deals with linear equations. And then in Topic 2, applications of linear equations, which deal with word problems. But we'll be moving on to Topic 3, and that's the only topic we cover in Chapter 7. So for some of you, you may need to review equations a little bit. It is available. So in Topic 3, we'll deal with ratio, proportion, and variation. And I think you know that only what we cover in class as part of our lessons will be on any test. So if it's not covered, you're not held responsible for things we haven't done. Okay, let's take a look at what is a ratio. Well, a ratio is basically a comparison of something to something. So one way to read it is A compared, in a sense, to B. A divided or over B, this would be its fraction form, and then A with two dots to B, or the ratio, that's what the two dots usually refer to, the ratio of A to B. But all of these are equivalent. And again, we use ratios in comparing units of measure. Now, in order to compare them properly, the units should have the same value. So let's go on. So looking at example 1, this is pretty straightforward. 5 hours to 3 hours. So you could write that 5 hours to 3 hours. Or you could have written it 5 to 3. Now, since they're both hours, there's no problem. That's just a straightforward ratio. Now, in example B, where it states they want 6 hours to 3 days, well, here you would need to convert hours, or I should say the days, to hours. So 3 times, in a sense, 3 times 24, which will then give you the ratio of 6 to 72. Now, again, generally, this is your basic ratio, but you'd want to simplify this and take out any common factors. Well, 6 goes into 6 once, and 6 goes into 72 12 times. So your ratio eventually here would be 1 to 12, or 1 over 12. Now, one place ratios really come in handy is when you're at the supermarket and you're looking at products that are on the shelves, and you're wondering which is the better deal. Well, often they have little tags that have this information, and it tells you for, let's say, 18 ounces what you're paying for 1 ounce. Now, as you look at it here, you can't tell that right away. So how would you do that? Well, you would set up a ratio. You'd say 179, or 8 I should say, divided by 18. So you're asked which size is the best buy. So you take your cost divided by the number of ounces, that's your ratio, and here it's about 10 cents an ounce. Now you would think the larger quantity would be the better price. Well, for this one, you're paying a little bit more than 10 cents per ounce. So between these two, this would be the best buy. But then when you went to the 40 ounce, again, setting it up as a ratio, figuring out your cost per ounce, here the 40 ounce would be the best buy. Well, I don't usually find the textbook incorrect, but I checked my math here a couple of times, and here the price is 0.095. So they're off here. And this one I had rounded off to 10, but the best deal, unfortunately, would be this one. So I may have to write the authors about that. But again, as you go to the supermarket, there is that little tag, and you wonder, what are they saying there? You may never have read it, but what it is what you are paying for by the ounce, or in some cases the pound, depending on how big a unit you're dealing with. Now it's nice to bring something into our course that we've covered in the past, and in a sense we have done this proportion before, that we said A is to B as C is to D. And we said that the first item up here and this last item, as you went in order, these were the extremes, and then this second item and the third item were the means, and this is defined below. So we say the product of the extremes equals the product of the means. So we can use this as we cross multiply, that AD equals BC, and we get this particular formula. So we will use that to figure out missing items, that if we have a ratio here and we're missing one of the items there, we can use a little bit of simple algebra, and we'll show you how to do that. There's the rule, and we'll go on to do some examples. Well, again, it's laid out quite well here. Let's just set it up that there's a ratio, and we're saying it equals this ratio. So if we cross multiply, 9 times x gives us 9x, and then 5 times 63 gives us 315. And now when you have something like this, 9x equals 315, the general technique will be to divide by whatever is with the x. This is called the numerical coefficient, or the number that's with the x. You divide by that, and you divide the other side by that. So, sort of a simple equation. Here the 9's cancel out, and you're left with an x, and you just divide 315 by 9, and you get 35. So again, this is the model you'll follow when you are solving an equation that's in the form of a proportion. A fraction equals a fraction. You cross multiply, and then whatever number is with the letter, that's what you divide by to get an answer. Now, as I mentioned, we skipped that basic section on solving equations. So we're going to give you a model to follow. This is a fraction on one side equals a fraction on the other. But we're going to practice this cross multiplication technique. Now, this division bar is also a grouping symbol, so we can replace that with parentheses here. So when we cross multiply, we're going to multiply 5 times this, which is what I set up there, and then 3 times this. Now you have to put what I have in parentheses, because now we're going to what they call distribute the 5. This will be a 5x plus 5 equals 3x minus 6. Now the general rule for solving an equation like this is we can take a term like 3x from one side of the equation and bring it over to the other side. When we do, it just changes its sign. So we get 5x, bring this over, is a negative 3x now. And then we want to take the 5 from this side, bring it over to this side, and on this side it changes its sign and becomes a negative 5. So to keep this a little clear, let's just get rid of what we've moved from one side of the equation to the other. And the basic rule we're following is we want all the x's on one side and all the numbers on the other. So on this side this becomes 2x, and on this side it becomes a negative 11. So we're giving you a quick review of solving equations. Now we divide both sides by the numerical coefficient of the x, that is the number with the x. So this is 2 times x, and we're dividing it by 2. And we divide this side by 2. So here the 2's cancel out, and you're left with x equals a negative 11 halves. And that's what they've done. And you've used some of the skills of solving an equation through the cross products. We're multiplying the extremes and the means. Now here's a case where they're going to use proportion to determine proper dosage of a drug. Now if you're a baby, how much penicillin do you give to a baby? How much penicillin do you give to an adult? How much do you give to a very thin adult or a fuller framed adult? As you can see, the dosage would vary somewhat. So this is often what the doctor will prescribe, and he writes that out in his prescription. He knows the size of the patient he's dealing with, or she's dealing with, and then accordingly. Well, how do they do this? Well, it's proportion. They figured out for so much this, for so much how much, and then you're just going to cross multiply here to figure this one out first for letter A, and then what would be the correct dose if it's 120 and it's packages of 100 milligrams in 2 milliliter vials. So let's solve this one first by cross multiplying, and it's set up here so we can just follow along with it. We're going to cross multiply, so we get 120x equals 600. Divide both sides by 120, we get x equals 5. So in the next place, next example, we have 100 over 2. What will 120 over x be? So again, the same technique. you're going to cross multiply. You get 100x equals 240 as you cross multiply. X equals 2.4. So 2.4 milliliters are needed. Okay, we're now going to do some other kind of proportions in which we're going to sample areas. Now, when I was a biology teacher and did some ecology work in the field, we would do population surveys, and we would tag fish, or the one I deal with, we were tagging eels, believe it or not. Anyway, let's take a look at this. So this is a very typical example that field ecologists might work on, that you are in a lake and you're going to capture randomly certain fish. Now what you do is you tag these fish. Put a little tag that doesn't really hurt them that much, but identifies them. Then you just release them all and let them all swim and mix up, and then come back at a later date and capture some more fish. Now, of the fish you now capture, you see how many had the tag and how many didn't. So this is the proportion we're going to set up. So on your first date, you captured and tagged 300 fish. Then when you came back a second time, you saw out of the 400 fish that you caught, 5 of them were tagged. So here the critical part is, how do you set up the proportion? Well, the proportion would be tagged fish out of a population, tagged fish out of a population that you didn't know at this time. So now we've set up a sampling, and we cross multiply, and we get that 5x equals 120,000. You can then divide by 5, and you end up with 24,000. So you could probably say, you may be off, but get a sampling that there are about 24,000 fish of that type in the lake you have sampled. And you did that by developing a proportion. Now you're getting 3 sets of numbers, and you say, well, where do I put them? And again, it's tagged to total population, tagged to total population. That's what sampling is. Now, another type of variation that we're going to run into is called direct variation. And there is a special formula for this. I always tell students when they're doing this, and they see that something's a direct variation, is write the general formula for direct variation, which is y equals kx. Now, k stands for the constant of variation, as you'll see as we go into this. But let's take a look now at this little chart. If you buy a gallon of milk, it costs this. 2 gallons of milk costs this. 3 gallons of milk costs this. So as you buy more and more gallons of milk, the price increases at a steady amount, and that is in nature what direct variation is. So you could write it, in a sense, your constant of variation here is what 1 unit costs, which is $3.50. Now later there's going to be another kind of variation, but we'll get into that a little later. Okay, so again, other words for this: direct variation, constant variation. So in the rule, they are featuring this basic equation: y equals kx, direct or constant variation. Now, if you solve for the letter k, which is often what we want to do, you will divide both sides by x, and you end up with what k equals. So in direct variation, this is the formula, and k, put this in your notes, equals y over x. That's what k equals. Okay. Now there is a protocol that we follow when we're solving variation problems. Step 1 is to write the equation of variation. Well, if it's direct variation, it's going to be basically y equals kx. Then they're going to give you a value for the y and a value for the x where we solve for k. Then, once we know what k is, let's say k we find is 5, we then write the equation of variation, which will be y. We replace the value of k with 5, and that would be what we are using as our equation of variation. So basically we want to find out what k is always, and then put it back in the basic form of, for this case, direct variation. So let's do a problem. So this is a very typical example in which they're going to use Hooke's law. It says that an elastic spring states that the distance the spring stretches is directly proportional to the force applied. So again, they're saying this is direct variation. So the basic formula is y equals kx. Now, what they've done here, though, is give you other words, or in this case, letters that we'll use to replace the y and the x. So what did we say this is? It says the distance a spring stretches. So we're going to say this is d, replacing the y with d, equals, now our k stays the same, we don't know that, is directly proportional to the force applied. So we're going to replace the x with the letter F. Now it says if a force of 150 pounds, so we know now, we don't know k still, but we know the force is 150, and it stretches at 8 centimeters. We now want to solve for k. Well, we're going to divide both sides by 150, and we get then k equals 4/75. Now, what will be our equation of direct variation for Hooke's law? Well, it will be d equals, we now have our value for k, which is 4/75, and then F. Now, this is what they will always ask, something like this. How much will a force of 400 pounds stretch the spring? So what we do here is we put our force of 400 pounds. And that will give us our distance. So if I went down a little bit, we'll see the answer, but let's work it out. So when I did it, I got 21.3 centimeters. Let's see how the book does. So 0.3 with a bar over it is 1/3. So our answers worked out well. All right, let's do one in regard to direct variation, where sometimes the value of x is raised to some power. There's an exponent. So let's take a look at that. So here we're looking at, again, in the basic form of direct variation, but now your x value is going to be raised to some power, but your constant of variation stays the same. And the example they're using here is the area of a circle. Area of the circle equals pi r squared. Well, we know that our constant of variation here will be pi, but let's look at example 5. So in example 8, we're again looking at another, and that was figure 5 that we referred to, direct variation problem, in which if we have a skydiver, it says from rest varies directly as the square of the time it falls. We disregard air resistance. So our basic formula would be y equals k, but now our x is going to be squared. And again, what letters might we substitute? Well, y is going to be distance. The k stays the same. And our x is time. So t squared. And that's what they have. Now we substitute. He will fall, or he or she, 64. So this is going to be 64 equals k. And it's 2 feet, this many feet in 2 seconds. So we put the 2 there, but now we need to square the 2. So this is going to be 4. So we get 64 equals k 4. Now we divide both sides by 4, and we get k equals 16. We now take our 16 and put it in our direct variation formula right here as a 16, and that's what you see. So the results, the variation equation, can be written this way. And there's what the protocol resulted in. Now they're asking how many feet would the skydiver drop to if the time were 8 seconds. So we have our basic formula. So d is going to equal 16 times t is 8 that we're going to square. So 8 times 8 is 64. So this will be 16 times 64. We get our end distance of 1024 feet. And we found it out by keeping in mind this was a direct variation in which the x was to some power. X turned out to be t, and it was the square of t. And this is the results. All right, we're now going to go on to look at inverse variation. So once again, as you read the problem, and they say it's inverse variation or inverse proportion, the formula that should come to mind is y equals k over x. So that as one item gets bigger, the other item gets smaller. Now, before we had, in just a quick review, y equals kx. And when we solved for k here, we got k equals y over x. Now here, if we solve for k, we're going to multiply both sides by x, and we get xy equals k. That is, we multiply both sides by x. Here they cancel out. So you can see the difference. This is direct, and this is inverse variation. So this is written up down here as well, a little introduction. So as we read example 9, they're talking about inverse variation. So again, a good idea might be, what is the inverse variation equation? And it was y equals k over x. Now as you read the problem, you're looking for letters that you would replace the x and y. The k stays the same. And here they're talking about the weight of a person varies inversely to the square of the distance. So in a sense, this would be an x squared here. But we're going to go weight of a person. Now our k stays the same. And then this is distance squared. So now it's a matter of substitution. And we have two different readings. I haven't seen these words in a while. An elliptical orbit, it's not quite a circle. So at the furthest point from Earth, that is its apogee. And then its closest point to Earth, that is its perigee. Some interesting words. Again, you can use your notes. What would the weight be? Well, they're giving us at the apogee, this person weighs 57. We don't know k, but we know the distance at the apogee is 6,700 miles that we need to square. So we're going to multiply, well, square this first and then multiply it by 57. That will give you what k is. And you're putting this in your calculator, just cross multiplying here. In a sense, this is 57 over 1. So k is the product of these. But now we're going to divide this product by the shorter distance that we square, and we see now at a shorter distance the person will weigh more. So further away you have less. In fact, if they get so far away, we say there is weightlessness. It's not that they don't have mass, but the attraction of gravity is so little, they have weightlessness. All right, let's go on now to joint and combined variation. So in solving joint variation problems, again, the basic form of y equals kx, this is direct. We just add another letter, c. So we still need to find the k. So here they're talking about the strength of a beam, 2 inches wide by 10 inches deep, is 1,000 pounds per square inch. What is the strength of the beam that is 4 inches wide and 8 inches deep? And we need to mention it's the square of its depth. So again, we're going to replace letters. We'll use the Y, we're going to use capital letter S. We don't know what K is. And then the X will be the W. And then the Z we're going to replace with the depth that we're going to square. So there's our basic formula. And now we substitute 1,000 for the strength, 2 for the width, and then the depth is 10, that's going to be squared. So this is 100 times 2, 200. We find out that K now is 5. So replace the K with the 5, and there's our joint variation equation. And now what will it be when the beam is 4 inches for the width and 8 inches for the depth? So we don't know what S is still, but we know this is 5 now. 5 times 4, and the depth is 8 that we need to square. So we have it laid out here. This is 64 times 4 times 5 gives you 1280. And we did it by using our basic formula, substituting carefully, finding out what K was. Once we knew what K is, we then substitute the new values to find our new strength. And this is something, again, you'll have in your notes, and if you have one like this, you would follow this protocol. In example 11, we're looking at body mass index, used by physicians to assess a person's level of fatness. And the way we do it is it varies directly as an individual's weight in pounds, and then inversely as the square of an individual's height in inches. A person who weighs this much and is this tall has a BMI of this. So here we're going to find out what K is in this formula and then apply it to a person that has this weight, this height. So let's look at it. So again, the general formula would be like Y equals KX over something. This would be a combination of direct and inverse. So here you see we're going to replace the Y with the B. We don't know the K, but the K is always in the numerator. The weight will replace the X, and the Z is replaced with the height that is squared. This is what over time the scientists have found to be a good measure of this. So we have this body index. We don't know the K. We're substituting the 118, 64 squared. Okay. Now we want to find out what K is. So we can cross multiply this, which gives us this, and then we divide by this, which gives us that. They did some fancy arithmetic here. So we cross multiplied and again got this. When we do this and put that in your calculator to check, we get 703. Now with a formula of 703, for our k, we then put that into what we had before, where our k is 703. We put the new weight, and then the new height, square it, and again, putting this in your calculator, this divided by this gives you a body mass index of 26, where they're asking us to round to the nearest whole number. You will know you have mastery as you do your homework and study plan and get your results. And again, all of this can be in your notes that you can use on your test. And good luck. And as always, if we have class time, we'll do some exercises.